When you install and launch Fantastic Integrity, the starting window will look something like this. It's going to prompt you to select the standard you're going to be using for new tests, and it'll ask for a license key if you've not installed one already. For our purposes, we'll be using NFPA 2001. This is what the program window should look like after you select the standard and enter your license key. This will be basically a new NFPA 2001-2015 test. In our case here, I've loaded a sample file, so we have data in here to review. This first section is the enclosure leakage design. This is actually a venting calculator. It's more of a design tool used to determine the design window for an enclosure. There's a minimum leakage required to relieve peak pressures, as well as a maximum leakage allowed to meet the 10-minute hold time. This tool will help you determine how much vent area you may need, or if a vent is needed at all. We'll go ahead and move on to the next section. The next section is test and technician info. This will just show the standard we've selected, as well as the technician and their certification level. There's 2 entry spots for a witness name, company, and a witness phone and email, basically just contact information. The next section is the equipment section. This is where you're going to tell the software what gauge and what fan you're using to run this test. In this case, we're using a DM32 manometer and a 6000 series fan. You can see here the fan serial number. The gauge serial number you can input directly based on the handheld that you're using at the time. The fan serial number is going to be tied to the software license by selecting the correct model. In this case, it's a 6000. By selecting the 6000, it'll give you an option to select any available serial numbers for that fan. We have one available. It's a single fan license in this case. The location entry is just stating where the blower door is set up. There are 2 fields for the gauge and fan calibration dates. For fire testing, gauges would need to be calibrated annually, so in this case our gauge does meet that requirement. Fans are on a 5-year calibration basis. The next section is building and agent details. This is where we're going to tell the software about the enclosure that we're testing, as well as the agent used and some of the conditions that'll be present during the hold time. We have some information fields about the building enclosure, including the building address and a field for customer details if any notes are needed there. Below that, showing elevation of the enclosure, there is a correction for barometric pressure. Our enclosure volume is going to be 30,820 cubic feet, so it's a fairly decent sized enclosure. This is typically calculated based on the floor area multiplied by the total height of the enclosure. It's going to be all the intentionally flooded volume. Maximum flooded height, usually this is measured from slab to the top of the enclosure. In our case, it's 9.55 feet. Minimum protected height is going to be 7 feet. This is the highest level of protected content within the enclosure. For descending interface hold times, the difference between these 2 inputs is going to determine the allowable drop, and the bigger this gap, the more leakage would be allowed. Moving to the right side here, we have enclosure conditions prior to discharge. Design temperature, that's stating the worst case minimum anticipated temperature that the enclosure should experience. In this case, we have it set to 65 degrees. And then below that, there is a bias pressure during hold time entry. This is the static pressure or bias pressure in the enclosure while it's set up in the hold time conditions. So basically the door fan would be installed and covered to seal the door, and then you're looking at the channel A pressure while taking a baseline, and we had a pressure of negative 1.2 Pascal. This pressure is going to force the agent out or pull the agent out of the enclosure, so any bias during hold time should be avoided if possible. Below that, we have the extinguishing agent info, the type of hold time calculation. Descending interface is what we're using, but there's also an option for continuous mixing and extended discharge. Continuous mixing would be if we are relying on the concentration level to determine hold time. If the agent is continually mixed with air, you have a starting concentration, and when this reaches a minimum concentration, your hold time would be over. In our example file here, we're using descending interface instead. We're assuming that the agent's going to dispense into the enclosure. It'll settle towards the bottom and form a layer. When that layer height reaches the minimum protected height, that's when our hold time will be over. We're using HFC 227EA for this enclosure with a mass of 1,147 pounds. Based on this mass, the volume of the enclosure, we are calculating an initial concentration. In this case, it's 7.6%. The initial concentration must be equal to or greater than the design concentration. If it's not, you'll get a warning stating that the initial concentration is too low. Design concentration, in NFPA they refer to this as minimum design concentration, but it is the target concentration for the enclosure. It's going to be based on the type of hazard. In our case, HFC 227EA, 7% would be a Class C. The specified hold time is 10 minutes in this case. That could be shorter or longer depending on what's needed for the enclosure. NFPA specifies a hold time sufficient for emergency personnel to respond. In this case, 10 minutes is our target. The next section down, after we enter all the enclosure details, this is going to be the total enclosure leakage section. We will be running the blower door and measuring leakage at 2 pressures in each direction and recording the flow at those pressures. The software is going to use this data to calculate a hold time. It's actually calculating a leakage area and a leakage rate, and then using that to calculate the agent hold time. At the top, we have 2 radial buttons here. The one on the left is going to be what's selected the majority of the time. If you were to select the other radial button, enter leakage results from a previous door fan test, you'll see that the window changes to allow you to put in a leakage area directly. If you wanted to use previous results to estimate a hold time or change conditions and see if there is an easy fix for a failing hold time, or just explore options, this is a great tool. We'll change that back to enter door fan test values. So below that, we have a date and start time entry box. We'll move past those. The operator location. This is stating where you're standing with the manometer. In our case, we were inside the enclosure with the DM32, and the red tube would be going through the door panel to the outside. The software knows that we are inside, and it also knows the channel A pressure. We're entering that directly as it shows up on the gauge. Those 2 things, the channel A pressure, either the symbol, either positive or a negative value, along with the operator location, is how the software determines what test direction we are running. Below that, we have temperature inputs, so it allows you to put in the indoor and outdoor temperature differential and makes corrections based on the difference between the 2. The entry below that is the bias pressure during fan test. This is the entry I was referring to in the last section. The bias pressure during hold time and bias pressure during fan tests are typically the same or very similar. You want to test the enclosure in the same conditions it would be set up in for a retention time or a hold time. And if you do that, for the most part, your bias pressures will match. If you have a situation where you have, say, an air handler that cannot be shut off for the fan test, but it would be shut off to measure bias pressures in the hold time conditions, that pressure would be present during the fan test, but not present during hold time. That would just be an example of why you would have different inputs in these 2 cells. So below that, we have our pressurization and depressurization set. The operator location and the channel A pressure, the top line shown here, pressure Pascal, those 2 inputs are used to determine which test direction. In this case, a positive channel A pressure plus operator location inside means the first set is going to be pressurization. If we were to change this to outside, you'll notice that the headings switch. Now it's a depressurization set, even though the pressures are the same. If you enter these as they show up on the gauge and put the operator location correctly, it should just populate automatically. So as I mentioned, this first line is the pressure line. It's going to be what shows up on channel A, or the top line on your handheld, on your gauge. That's going to be copied directly over along with the fan pressure